It's Teardown Tuesday, where we take things apart and kind of see what makes them tick. Today we have something that many people probably don't see much of these days, but they used to be quite common with security systems. Let's check it out. Today I figured we'd look at this little emergency light, a safe house emergency light. This was sold by Radio Shack. So right down here, Radio Shack, Tandy Corporation. And it's a light that flashes that typically would be connected to your alarm system, so that after your alarm went off and reset itself, the light would continue to flash so that you are alerted, and so that the authorities are alerted to where that siren is going. You know, your alarm system goes off, and after the siren resets, until the alarm is actually turned off, the light would continue to flash. And they came in various colors. I think I've got a couple of other ones kicking around here from when I did a video many years ago for an alarm company. And he gave me some products to show off. And a couple of them were red and blue strobe lights, although the amber ones were ones sold by Radio Shack. Now these today are still around. The ones that you see today are going to be LED lights. This is a little different. This is actually a real strobe. It's a xenon strobe light, just like you'd find in a camera flash. So when I power this thing up and it works, it will blink. About 2 flashes a second. And you can see it's pretty quick. It catches the camera shutter. It's so quick. So let's just take a look at how these things are put together and what's in them. Because I think you'll find that there's more in here than you think, and you're going to see some components in here that you wouldn't think that you would see in something like this, such as the timing circuit, for example. There's many ways to time that flash, but they've used one of the simplest timing mechanisms that you're ever going to see. So here's the flash tube, the xenon flash tube. It's a high energy device. Typically takes a couple hundred volts across the electrodes, and then a trigger voltage of a couple kilovolts to trigger it. So inside here there's going to be a power supply to step up the 12 volt supply to about 150 or so volts for the flash tube. 150, 160, I don't know what the minimum of this one is. It's probably more like about 180, because this is a fairly good size flash tube. And then there'll be the timing circuit, and there will be the triggering circuit. So let's take a look at what's inside this thing, and we'll take it apart and show you guys what's in it and how it works. I think some of you might find this interesting, and others are just going to say, what the hell? But what the heck, eh? This is a teardown video today. So take off the reflector, and here is the circuitry. And as you can see, there's a lot more in here than a lot of people would even think would be in something like this. And you've basically got two totally different circuits. So over here on the left we have our power inverter. So this is just going to be an oscillator and a little transformer, and this transformer is going to take the AC 12 volt signal that is being passed to it from the DC inputs. So the AC signal, or a chopped signal, is going to be created to the transformer. So basically this transistor is going to be switching off and on at a high rate of speed, maybe 20 or 30 kilohertz, but it's going to be running at a relatively high frequency, and that's going to derive the higher voltage in the secondary, which is going to get rectified by a rectifier diode and stored in this relatively large 22 microfarad 250 volt capacitor. Now I'm going to make sure that this is discharged, because I had it running and this thing can store some voltage. Let's just see if it has stored anything. There should be an internal discharge resistor that will discharge this capacitor once power is removed, because you don't need a capacitor with a couple hundred volts sitting there waiting to bite you. But let's just see if there's any power left at all in this cap. And it's discharged, as you can see. But if this was operating, this would be running at probably about 180 volts. What we'll find is that this capacitor is connected directly to the terminals of the flash tube. So one will be connected to the positive terminal, and the other one will be connected to the negative terminal. So The capacitor is connected directly across the flash tube. It's also providing power to charge up the timing circuit, which is this circuit over here. How this timing circuit works, and it's really quite simple. You have a capacitor that's going to charge. Actually, you have two capacitors. You're going to have a capacitor that's going to charge, and that would be this one here. This one charges up as well. This is your kicker. This is what discharges into the little transformer, a little step-up transformer that generates probably around 4 kilovolts of pulse, which is applied to the trigger electrode. And you'll see a fine wire right down here. That is likely the one. That might be the trigger input between, this would be the ground input for the trigger, and then this is the high voltage that's connected over to this lead. We can confirm that by just measuring it, but I'm pretty sure that that's probably this one, which it is. So what happens is, as this capacitor is charging, this one is also charging as well. Over here we have an SCR, and we have the neon lamp. And you're wondering, why is there a neon lamp in here? Well, this is what actually fires the trigger coil. Second capacitor over here also is charging, and this one here is connected across the neon lamp. Once the capacitor reaches around 60 to 70 volts, which is the breakover point for the neon lamp, it will ionize the gas in the neon lamp, which will, of course, jump across the gap here in the neon, and one side of the neon lamp is going to be connected to the gate of the SCR, which will then, of course, turn on this SCR. The SCR will then dump its charge from this capacitor into the coil, and, of course, as soon as it dumps its charge, the energy from this capacitor is going to be dissipated, and its charge up voltage or its charge up limit is through these resistors, but its current is going to be, or its stored energy will be completely discharged into the trigger coil, which will cause it to conduct quickly, dump a large magnetic field into the coil, and of course the capacitor is now discharged, so the magnetic field will collapse, and when the magnetic field collapses, you get a pulse, comes out the secondary side and into this inductive, and this is on the outside. This is a ring on the outside. The energy comes in as a pulse here, which causes the gas inside to ionize, and you get a flash. If you notice, it looks like there's something on the inside here. Well, I think that's just conductive paint that's actually on the outside of the tube. It is. It's just conductive paint. That's to ensure that the pulse ionizes the gas all the way around and causes discharge. The xenon gas inside the flash tube ionizes, and then all the energy stored in Mr. Capacitor over here discharges through, and you get a bright flash. That's, in a nutshell, how they work. Let's pull this little circuit board out and take a look at the bottom. Remove a couple screws. You have to unsolder these pins here, the power pins that are pushed through here. Made in Taiwan. And here we see, as I said, this is how I said it was going to be connected. Here's the trigger coil going right to the secondary of the trigger for the trigger grate or plate. We have our B plus here. B plus is going in through a diode here, first of all, to protect it from somebody wiring it backwards. So there's a diode here. This is just for protection. There's a filter capacitor across here, and it goes into the transformer. You can see here, this is our positive lead. Goes into the transformer, and the other side of the transformer comes down, and it's connected to the collector, I believe, of this transistor. And there's also a resistor across here. This resistor across here is going to the base of the transistor, which will turn the transistor on and allow current to flow through the transformer. It's also going to operate, there's another resistor across here and a capacitor, which creates the oscillation circuit, which causes this transistor to oscillate at a high frequency. We can actually put the scope on there and measure what frequency it's operating on. And of course, here's our secondary side of the transformer here. One side is connected to ground, as you can see. This side here is grounded. It connects to the same terminal as the B minus. And the other side of the transformer goes over to this diode over here. And there's a center tap of the transformer, which is also used for feedback. It connects in through another resistor and a little diode over here. This is also used in the oscillator circuit. So as pulses are created through the transformer, this is what operates this transistor to turn it on and off. It's charged up. This is the secondary diode here. Here is what charges this up. And the positive terminal is connected to this terminal here. So it's actually the positive side of the secondary is actually connected to the ground side. So this diode will be giving us a negative regulation. So this is negative with respect to ground, right, which is the positive side. You can see here, if we're looking at this, this is marked with a plus for the positive side. That's the positive side of the high voltage, but that positive side is actually connected to the ground side of the input voltage, the low voltage side, grounded to this. So this is negative. So this is actually a B minus with respect to ground. Flash tube is over here, and this negative circuit also goes down to the SCR. The SCR is connected through to, this is the, where's the trigger wire? This is the trigger wire here. This is the capacitor. That blue capacitor is right there across this trigger wire, which is also connected to the SCR. Now obviously the speed that the strobe is going to operate on is dependent on how quickly we can recover the power to the main filter and the timing circuit. The power recovery is determined by the size of the transformer and of course the current handling capabilities of the oscillator transistor. Larger strobe lights, like used for party strobes, for example, are charged up from your main AC line, typically using a voltage doubler setup, and can recover a lot quicker. So the faster you can recover the charge in your main discharge capacitor and your timing circuit, the faster you can run them. But they all basically operate under the same principle. I built a strobe light that was a lines powered when I was probably about 10 or 11. Got a good couple jolts out of that thing because it used 2 caps and a voltage doubler array to generate around 350 volts, and I got belted by that a couple times over the years. But a very similar circuit didn't have this. It was just this side of it, and of course a voltage doubler that went operate off of mains. These ones here are designed for the security system. They're designed for that single flash rate, and this is very similar to the circuitry you'd find and the charging circuit for an electronic flash for a camera. When I apply power, try to do this without electrocuting myself. When I apply power to the unit, it flashes. Pretty simple little circuit. If we were to monitor the voltage, in fact, if I want to see how many volts this thing actually charges up to, I could disconnect the flash tube so that the flash tube itself does not flash, and then we could measure the actual voltage that the capacitor charges up to. So I'll just discharge any residual charge in the cap, and if I disconnect the trigger coil here, I can just unsolder one side of the trigger coil, then it won't flash, and then we can actually measure the voltage. The trigger will still try to provide its spark, but it won't do anything. Once I get it unsoldered, that is. There we go. So now when I connect it, this is going to have lots of voltage, probably even spark. It could even arc from here, but we'll apply power, let the circuit charge up, and then we can measure the power on the capacitor. So let's apply power here. Gotta keep my fingers clear when I do this so that I don't zap myself. just so I can get this clipped in here without it running. Okay, now when I turn on the power, the capacitor will charge to full power, but because the flash tube is not running, it won't discharge, and we can see how many volts this unit operates at. So capacitor is charged. You can see the neon lamp is flashing. You see the neon light is blinking there as it's producing its high voltage kick. But if we monitor the voltage here, we'll see that we have 230 volts is what this capacitor is being charged to. And all we need to do is get that kick to that flash tube, and it will go. As you can see, the oscillator here is still going because the capacitor is still charged, and until this capacitor discharges, this oscillator will keep running and the light will keep blinking. So right now this is still producing a kick. And if I were to connect this lead, it would probably flash. If I can get a good connect. Oh, it stopped. So let's just start this up again. This should make it flash. Right? Now if I just, even though the capacitor is charged, if I touch it here, it'll flash once as it discharges the stored energy. There's a good example. You see, lights flashing away. Power off and discharge what remains in the cap. Anyway, that's this little unit here. Will just discharge any residual charge that may be in the filter cap, the main storage cap. Okay, that is now completely discharged, so it's now safe to handle. That's going to do it for this one. Just a little quick demo on how these little devices operate so that you get a better idea of what the older strobe systems looked like. As I say, I know the new ones that they're putting in on systems these days, they're all LED based. We don't see these old classic circuits used too much anymore. It's just because of the cost, right? It's a lot less money to have a couple of LEDs and a little controller IC that will flash them than it is to have all this circuitry and high voltage and a real flash tube. Anyway, this was going back together because this is still a good unit that is functional and can be used. So I'm going to reassemble this unit, and maybe someday it'll find its way back in to a security system somewhere. Anyway, thanks for watching. We'll catch you in the next one. Bye.